Okay, hello once again, and I think we can start now. We have 24 participants on this live webinar, and I think it's pretty good for now. I'll start with a little introduction about what we will be doing today and what is Exonum framework is. So first of all, let me introduce myself. My name is Ilya. I am a Rust developer at Exonum team. Actually, I'm working at Java bindings department, and we are working on bringing support for Java language into Exonum framework. Exonum is a modern, safe, and fast blockchain framework for private blockchains. Using Exonum, you can develop secured distributed ledgers, secured blockchain applications for different purposes, including e-voting, e-auctioning, cryptocurrencies, and so on. Today, we decided to talk about developing a pretty simple e-auction Exonum application called Exonum CryptoAlls. Once I've already showed the process of developing this service using Rust programming language, and I have some experience in implementing this particular service. But today we decided to use Java programming language instead of Rust. First of all, Exonum is entirely written in Rust. We have more than 100,000 lines of code in Rust, but we found that Rust is not the easiest language for blockchain developers. Because it offers some very modern features that are not existing in other programming languages. And developing a blockchain service in Rust may be hard for newcomers to understand at the same time new topic, blockchain development, new language, Rust, and new framework, Exonum. So, as I said, we decided to use Java for this education session. Java is well known, pretty simple, a bit verbose, but still very good programming language. And we have a full-featured support of it using special project called Exonum Java Binding. You can find all our projects on our GitHub, github.com/exonum/exonum Java binding or /exonum. And you can find all the necessary documentation for developing new blockchain application on our website, exonum.com/doc. And here you can find a Get Started menu item. And at the end, you can find Java Binding User Guide, which contains all the necessary information to install, set up Java bindings, to create a new project, to develop it from bottom up. And today I'm going to show you how to use this project. So what we are going to develop today? Yeah, actually, a pretty good question. So in our GitHub organization, we have a special repo called CryptoOls, Exonum CryptoOls. It's a demo of simple blockchain game based on e-auction economy. And it is written in Rust and in JavaScript. But yeah, so everyone can just download necessary everyone can just download necessary libraries, compile and run Exonum blockchain with this service, and then run a front end, on your local machine, and you get something like this. Here you can see some owls with different appearances, with different names, with different DNAs, and of course with different owners. In this front end, you can actually explore your blockchain. You can see all the transactions that proceed in this blockchain. You can create new owls by choosing father and mother, and this owl will appear in the list of your owls, and you can choose one of your owls, enter some price, enter duration of auction, and create new auction. So another user may log in, find your auction in the list, choose it, and make a bid for buying your owl. So the more so the bid with the most value wins, and all this system is securely controlled by blockchain. It allows you to verify the history of transactions, to make sure that the information in your database was not altered by anyone, and the state of your database is absolutely correct. So yes, we have a Rust example, Exonum CryptoOls, and today I want to develop a Java application with the same backend, with the same backend API, to use it with existing front end. Okay, so let's start. I've already installed our Exonum Java application using instructions on this page, exonum.com/doc. And now I can create a new project. So I will just show you how to do it. Yeah, one moment. I just need to stop my blockchain with Rust CryptoOls. Okay, so now I can just copy this command from our documentation, paste it. Marvin will download archetype for our blockchain application, and we need to enter group ID. I will choose Exonum examples. And artifact ID, it's a unique name for our future service, and it will be just auction. And we need a version. I will do 1.0.0. Package is OK. And so now we have a directory called auction with our project. I can open it using IntelliJ IDEA. And we'll see the main parts of any Exonum application. So yeah, the core of every Exonum application is called class service. Historically, we call all our application services. In other blockchains, you can often use word smart contracts. Actually, smart contracts and services are pretty equal. They have the same purpose. And this class is used to define the high-level interface of our future application. So we need to provide a unique service ID, which is used by framework to determine what service will be used to proceed specific transactions. We choose a specific name for our service at the auction. We have some initial service configuration in JSON format. It will be written inside a database after the creation of the first block of the blockchain. But it's actually not necessary. Here in initialize method, we just return our initial service configuration. But again, you can use it for storing some data needed for your application. We will not use it in this service. So to develop any Exonum application, you need to define only 3 modules. You need to define your database scheme. It's the structure of your database. It's a scheme of all your structures that will be stored inside Exonum blockchain. Also, you need to implement your business logic. Business logic is implemented using transaction messages. I will show you them later, but to use transactions, you need to tell framework how to handle them. And so you need to implement toTransaction method in transaction converter class. The last thing, but probably most important one, is to implement a specific API for your service. In Exonum, we use HTTP servers for our Node APIs. In Rust, we use Actix Web library. In Java, we use well-known Vertex server for public API of the services, but at the same time, we use Actix as a part of a Rust implementation of Exonum framework. So we have some question. Let me check. So here you can see a pom.xml file. All these files were generated automatically using Maven archetype feature. So here you can see the list of all necessary dependencies for our service, including dependencies for testing, such as Hamcrest and Mockito. And you have a pretty basic configuration for packaging your Exonum service into a single jar artifact that will be used while running Node with Exonum blockchain. So I created this project just to show you the basic structure, just to show you the auto-generated code for Exonum MyVNet type. Yeah, by the way, the tests are also automatically generated, and we have a framework inside framework called TestKit for testing your service in an isolated environment. You can send some transactions to your service. You can verify the state of your database. You can send API requests, and TestKit TestKit supports most of the features of Exonum, but of course it's hard to test some complex business logic, because in the real blockchain network you have from 4 to 20 nodes, but TestKit is only capable for testing one specific node, and some complex features like Bitcoin anchoring is not working there. So again, we need to implement our database scheme. We need to implement our business logic, our transactions, and last part, we need to implement our public API using Java Vertex server. So now I will close this newly created service because I've already prepared another project called CryptoOls, and I've already written some boilerplate code here. I just expanded the auto-generated code. So now you can see that we have a different service name, same ID as was auto-generated. We have some initial service configuration, which is pretty useless here. We have a special method called create public API handlers, which is used to initialize our public node API, and I will show it later. In our project file structure, we have several modules. We have a pretty large class called scheme, which contains about a dozen of methods that describes the structure of the database that we'll use. We have a transactions module with 4 transaction classes and a simple module for error codes. I will show you in detail a bit later. We have a module to represent our structures in a more suitable way with proper setters and getters. I will explain you why we need it a bit later again. The last part, the most important, we have our API module with API controller that binds specific functions to specific API endpoints. And I will show you how to handle it later. So now we are going to a special directory called proto with only 2 files, model proto and transactions proto. So let's briefly look through them, and we'll try to understand what they're for. Yeah, I need to change my screen just to read through questions that you're asking. Yeah, the question, will this Java auction service work in parallel with Exonum Rust backend? Actually, yes, you can run both Rust and Java services at in the same blockchain. It's supported, and here I use it because I need a time service to get a current time in the blockchain. And time service is written in Rust, and I successfully use it through Java. So let's look through our model.proto file. We use protobuf to serialize and deserialize our data that is stored inside blockchain. And we need to define some helper structures. So here we define a message hash, which is just a sequence of bytes, public key, which is also a sequence of bytes, but we have different types for readability and robustness. We have crypto-OL structure that represents our OLs. So each OL will have some name in string, some DNA, which is 32-bit wide integer. Of course, it will have owner. Each user in our blockchain will be represented by a single public key. It's pretty easy to use and pretty powerful thing. So I can't think of a reason to use a more complex structure to represent our unique users. So all will contain a field called owner with a public key of the owner. And with a timestamp type provided by Google protobuf library, just to store the time of last breeding of our OLs. We'll use it in our business logic to verify that user will not be able to breed our OLs too fast. So together with the public key of the user, we'll store some additional data just to show a nice interface on our front end. So we'll store the name, the balance, and another field called reserved. It is used in business logic of our auction systems. So once the user makes a bid for some OL, the amount of money that is in this bid will be reserved, and the user will not be able to spend it. Will spend it before the auction is closed. So auction bid is pretty simple. It contains only a public key, which identifies the author of this bid and the value of bid in our virtual currency units. So let me check answers. Questions and answers. Yeah, okay. So the last structure that will be used in our database is called auction. It contains public key, the unique identifier of all in this auction, the start price for this auction, duration in seconds before this auction will be closed, timestamp to store the time at which the auction was started, Boolean closed flag, and a special field just to verify the integrity of our database. So here we will store the Merkle tree hash of our bits collection, just to verify that no one will hack our database and exchange bits afterwards. So I will explain how it works while we will be implementing our business logic. So now let's talk about our transactions. The user can create and send a signed message called transaction with some data to the Exonum blockchain. This transaction will be handled by the framework, by your service, and this transaction will trigger some function containing the business logic of your blockchain. So yeah, about sources of this project, this is not on GitHub yet, but we will definitely post it after this webinar. And also we'll send you an email with the recording of this webinar just in case. So we'll have only yeah, this one is not necessary. We'll have only 4 transactions. The first one, called create user, pretty obvious. The client will send this transaction to add new user to the blockchain. We'll send just the name, and our business logic will just fill all other fields of the user structure afterwards. We have a transaction called create all. We will use some fancy business logic to combine the DNAs of both mother and father of this all, and this way each all will have a unique DNA based on the DNAs, so the appearances of its parents. Create auction transaction is called when I press this create auction button in the front end. So it just contains the fields that are sent that the user chose here. And the last transaction, make bid. Again, front end will send it while the user jumps on some auction and makes some bid to buy some all. Okay, so let's go to our database scheme. And here I will show you how to define the structure of our future blockchain database. So to do so, we need to implement some methods. For example, this method is called getAlls, and it returns a type called proofMapIndexProxy, which is actually can be seen as a hash map with some fancy Merkle trees on the low level. So you will be able to verify the integrity of this hash map using functions that are provided inside the Exonum blockchain. So this map will have a keys of type hashcode, and we'll have values of type crypto-all. Model protos is an auto-generated file. It's actually an auto-generated file from these proto definitions here. So we have a crypto-all protobuf message, and Maven protobuf plugin will automatically generate a specific a specific class for our crypto alls. So how can we create such type? We need to provide a unique name for our index, because Exonum uses RocksDB on the low level, and RocksDB is a key value blockchain, not blockchain, but general database. And it can be represented in memory as a simple hash map structure. Yeah, I will answer some of the questions a bit later. So we create a unique index name by concatenating the name of our service with underscore and a specific identifier we provided. So here you can write proof map index proxy, new instance, and you need to pass index name. Here you need to pass a view to your blockchain database. The view is provided through the constructor of schema, and it will always be available when you need it in your transactions, in your API endpoints. And after that, you need to provide to explain Java what types you're actually using in your database, what serialization and deserialization mechanics you use. So you need to provide one of the instances of standard serializer for your keys. So here we have hash code. That's why I choose standard serializer's hash. And you also need a protobuf standard serializer, which is initialized with a specific class that we use here. So we use crypto_all, so we need to use crypto_all as the argument to protobuf standard serializer. And yeah, actually that's all. How you will use this method? So in any of your transactions, let me show you. So transaction, just a class with a specific function called execute with argument transaction context. So you can just create new scheme using transaction context get fork, and later you can call scheme get alls, and you'll get specific proof map index proxy here. And later you can just use some methods like get, and you can pass a key as a hash code here. And yeah, and get returns the model protos crypto_all class, and you cannot work with it because it's auto-generated and you need to convert it. So that's why here I have some pretty boilerplate classes with some private fields and with a simple constructor, overloaded constructor that accepts model protos crypto_all class and transforms it into more usable class. with specific methods. So let's return to our scheme. And here you can see all the methods that we will use in this service. Let me explain. So, for example, we have a method called getUsers that again a map index of not hash code but public key and specific class called model process user. It's again auto-generated from our protobuf definition from this protobuf message. And again, we write a specific type. Here it is map index proxy because we don't need fancy MerkleDB structures under it. We use center serializer's public key because our keys are not hashes here. And again, standard protobuf serializer. So the same thing happens with actually all of these methods. They're pretty boilerplate. It's a bit boring to write them, but it allows you to control the serialization mechanics in your blockchain database in a very flexible way. So here you can see another method called new in group unsafe. Why do we need it? So I want to represent a collection of collections. I want to return the list of all users, the list of all alls owned by the specific user, and unfortunately, protobuf and therefore Exonum will not allow you to just create some deeply recursive structure like this. So together with the index name, you need to provide the second key that will be determined. Using this key, the path to the value stored in the database will be fully determined. And you'll get, instead of specific collection, you'll get a collection of collections. So for such methods as getUserAlls and getActionBits, I use exactly this method. I provide not only index name, but also some unique identifier in the format of bytes. Yeah, so our scheme contains about 100 lines of code, and it's all that you need from the structure for the structure of your database, but also you need some business logic to work with. So now let's take a look at our transaction converter class. So for each service, you need to implement such class with a toTransaction overloaded method, overrided method. And here I use map from ID of transaction from the unique identifier. So for create user transaction, identifier is 0. For create all transaction, identifier is 2. And the front end will need to pass this unique identifier inside the transaction message. So transaction converter then gets transaction ID out of message looks through the list of all our available transactions and applies a specific from row transaction function that we implement in every our transaction. So from row transaction method is pretty simple. We just used, again, a standard protobuf serializer with transaction protos create user class in this case, and just deserialize it from bytes payload that's stored inside every transaction message. Okay, so what is it? Yeah, nothing. Now let's take a look at some of our transactions. For example, create user transaction. This transaction has a single parameter called username with a type of string. And to implement transaction, you need to implement a method called execute, which argument transaction context. Each transaction context contains very basic structures for your business logic. For example, it contains the author, the public key of the transaction author. It contains a mutable view to your blockchain database, and you can use it to construct your schema with. Yeah. Yeah, it contains transaction message hash method, which can be used in some business logic applications. Each transaction as Exonum is unique and uniquely determined by its hash. So it can be useful, for example, for testing when you need to verify that exact same some specific transactions with specific hash was executed successfully, for example. So how you implement the actual business logic of your transaction? It's pretty simple. You need to implement error handling to parse the inputs of your transaction to verify that your transaction is valid in terms of your business logic. If it is not, you must throw a transaction execution exception from this method. And transaction execution exception takes some specific integer that represents the internal error code of your application, and it can also contains some string for debugging purposes. So here you can say that here you can see that we get the table with all our users. We get a user with a specific public key, and if we succeed, so this user is already exist in this in our database. If this user is already registered, we just return, we just throw transaction execution exception with specific error code, and we can actually write some debugging information for us just to spot it in logs, for example, and not convert specific error code to specific error, business logic error, or manually. So error codes is just a simple class with some amount of static fields for all possible errors in our business logic. Yeah, so after handling all possible exceptions, all possible errors with arguments of your transaction, you can actually make some changes to your database. To do so, firstly, you need to create some structure. Here, I create a new user with a specific name. And using method put for our getUsers collection, I set a specific user in protobuf to a specific public key. After that, after creating a new user, I actually need to create two alls for it. So as you can see, initially each user has two alls called username as Eve and Adam. So there are different methods to create new alls for our users. Here I use a simple one. I just have a specific method that creates new all, puts it into database, and I update some helper tables that are used to handle connections, the connections between different pieces of data inside our blockchain. The another more complex, but maybe more flexible way will be to generate a specific transaction, and that I use to create all and send it to the blockchain. It will be executed. But for simplicity, I choose this specific way. Okay, so now you can see that, for example, make bid transaction has a far more complex business logic than create user one. So here you can see that I need a current time of at the moment of transaction execution, and I have a special method in helpers class called getCurrentTime. So let's take a look at it. It's actually related to the question about using Rust and Java services together. So getCurrentTime method accepts the view into our blockchain database. We use a specific type from Exonum Java binding time library. We create a scheme, so time service written in Rust, and it of course has its own scheme as we do in our auction service. And we create this scheme using a provided view to blockchain. We use a specific method on this scheme called getTime. And here's this important moment. Time service is implemented in a way that it consolidates the time from different validators. And for the very first moments of blockchain start, this time is actually not available. because the validators are not yet handled the very first transactions and haven't verified the exact time of block acceptance. So for the first few blocks, we will actually get a transaction execution exception from this method with the error code time not available, and helper message time service not yet available. If it's not the case, I will just return a zone date time in UTC time format with a UTC time of zone offset. So here you can see that I have a lot of comments that describes the error handling in make bit transaction. It has a lot of conditions, and each conditions must be verified manually. So it's actually pretty. It's actually a lot of boilerplate here, but of course you need it just to verify that the front end, because the front end can send invalid transactions, because the front end is unaware of the state of your database. Yeah, and you just need to check all these conditions. So here I check that our user actually exists. I check that the auction that we are bidding exists. I check that this auction is not yet closed, so we can actually take another bid on it. I check that our author of transaction has enough funds for this bid, so the amount of balance is more or equal to the value of this bid, to the argument of this transaction. We have a specific error for the case when we are trying to bid for our own auction. Of course, it's not permitted in our application. We get the highest bid out of our database. So here I use schema get auction bids. For a specific auction, I get the last bid out of collection of them. And if it's not found, I just take the start price of this specific auction. So if no bids were made before, we'll use just the start price. Provided by the users. So here I cannot use front end because I actually stopped the backend now. So after handling all these possible transaction execution exceptions, all we need to do is to update our blockchain database to set specific structures to specific keys, to add a new bid to the collection of bids for the specific auction. So it's pretty simple and pretty boilerplate. The nice part of implementing breeding process of new OLs is that we have two parameters, father and mother DNAs, that are represented by a simple 32-bit integer. And we also provide a unique hash just to get some randomness in our blockchain. So as you probably know, random numbers are very difficult theme in any blockchain. And to use them correctly, you need to initialize your random generator with some numbers that will be exactly the same on different nodes while proceeding the transaction. So here I use a unique hash value. Yeah, and we can take a look. Yes, so here for unique hash, I use the Merkle tree hash of our alls collection. So each proof map and proof list has a specific method called getIndex hash, and it returns a unique hash of the collection states for this moment. Okay. So how our business logic of breeding alls is implemented? I use a Java bit set to convert our integers to bit vectors of size 32. And I use a pretty simple loop through all the bits in DNAs of father and mother. And the algorithm is the following. If the bit in father's DNA equal to the specific bit in mother's DNA, then with the probability of 80%, we just use the same bit, and with the probability of 20%, we invert the bit of the parents. Otherwise, if we have different bits for our mother and father, for example, mother has zero and 1 1, and father has 3 zeros. So the first one will probably be 0 with a probability of 80%, and second and third bits will be 0 or 1 with the equal probability of 50%. So it's not the thing that is much related to blockchains. I just wanted to show you how to handle these situations when you need some random value, and just to show you how to implement a pretty simple variety of shapes and appearances of alls using just one integer value. So our front end will convert this integer again into a sequence of bits, and will adjust the appearance of each all using SVG file. Using SVG file with all possible appearances. Okay, so after implementing our transactions, our database scheme, we need to implement our API endpoints that will return some information for us. So in Java bindings, we use, as I said before, we use the famous Vertex Java server. And the process of binding specific endpoints to specific requests, blockchain requests, is not much different from any other backend application. So here you can see, for example, a get user endpoint, and Here, I just create our scheme using provided view. I get a public key from the request, from the pub key argument of the HTTP request, and just return the specific user in JSON format. So the front end will handle it and display in the nice way on the user interface. So after implementing all the parts of our service, of course, you need to run it. So let me just revert the changes that I made before. Yeah, here we have a fully working crypto-alls service. We have also some tests for it using test kit, and now I can just type Maven test, and all classes will be compiled, and all the integration tests that I have will be run. So let me show you quickly one of the integration tests, and then I will show you how to actually start our created blockchain service. Okay, let me choose the simplest one. Yeah, so here we use a JUnit test framework for Java. We have a special JUnit extension for our test kit, and we create just a new test kit with our service module. And we have a bunch of tests in this test case. So for example, here I test that on creation of our blockchain, after creation of the Genesis block, the method getAlls will return just the empty collection of alls, which is pretty straightforward. So again, we have a test kit as a transaction context here, and from test kit we can get a snapshot for our database, we create our scheme, and we use our method and assert some invariants of our database state. So test kit supports far more complex methods, for example, far more complex stats. For example, here I construct a specific transaction message by passing service ID, transaction ID, binary payload in protobuf format, signing it with specific public and private keys. And later I create a block with this transaction message. And I verify that state of our database is pretty expected. So talking about running our blockchain application, yeah, I need to show you in our documentation on website. At the end, you can find two sections: how to build service artifact and how to run service. And here you'll have an explanation how to enable Rust, specific Rust services together with your Java service. So I created, I created a file called services.toml in the root directory of our project. Here I wrote just two standard Rust services. One is a configuration, which is used to update blockchain configuration, for example, to update the consensus configuration on the fly without stopping the nodes, and time services, which is used to get a very precise and secured time consolidated from every validator in the network. As a user services, you can pass any amount of Java written artifacts. And here we have a Java crypto all service. I have a path to this artifact that is created by running Maven package. Again, I haven't changed our POM file, so this stuff is auto-generated. You don't need to write it yourself. We're running just Maven package. You'll get your working service artifact. And the process of initializing and running blockchain node in Exonum is rather complex because we support a secured way to run nodes without exchanging private keys of different administrators. So it can be a bit complex for newcomers to use at the first time. Here I have a small bash script that triggers specific commands. So I generate all parts of public and private nodes configuration. And after that, I just trigger run, pressing a specific generated node config. So actually, we can see it here. We have a consensus configuration, validators keys. So public. So it's the public keys of every validator nodes in our blockchain. We have some external IP addresses for our nodes to communicate between them, and some basic network configuration. Some of these parameters can be changed by user, but some of them are stored inside a database, so you need to get to a consensus with other administrators if you want to change them. And yeah, at the end, let me just run this node. So we have some debug stuff going here, and let's wait a bit while our Java runtime is initializing and Vertex server is started. And here you can see that our blockchain is up and running. It consists of only one node, but here you can see that the height is constantly increasing, so blockchain is good to go. And now it is available at our local host, so I can just send a specific request using Siuru, and I guess I will be right while writing it. So we use 7000 because it is the EGB Exonum Java binding port number provided for our run command. And with a specific path of API service Java crypto-alls, where crypto-alls is the name of our service And the last part is provided in our API controller. So here we have v1/users endpoint, and it's not working. Let me check it. Yeah. So where was mistaken? Crypto alls. Oh yeah, here. I need to write services instead of service. Yes. Obviously, we have just an empty array here because we didn't add any users to our blockchain, but well, actually we can change it pretty quickly, and we can, for example, alter the database state in our initialize method to add some user, and it will be displayed here. So I guess that now it's time to answer the questions of our attendees. So answered. So okay, so you can will this Java auction service work in parallel with Exonum RAS backend? It can. It works with two RAS services, configuration and time service, but it's pretty easy to combine standard RAS services and your custom Java services. It's not yet possible to add some specific RAS services without changing the source code of Exonum Java binding project. It's not hard to do, but it requires some time, and especially some time to compile it. But I guess it's pretty straightforward task to do. And of course, you can combine both Java and RAS services in any of your blockchain applications. Okay, so I've already answered about sources of this project. They will be available. I guess we'll send a specific letter for with the link to it after it will be published. And after the front-end part of this example will be updated to suit with Java backend. It's not clear how Exonum call Java part. So it's not clear. I agree with you. Exonum Exonum Java bindings uses a GNI library and loads the Exonum dynamic library using standard Java features. So the Exonum is a dependency of a Java application, Exonum Java binding. But the thing that complicates this scheme is that actually we have a Exonum Java application written in Rust, which parses the configuration and runs Java virtual machine, loads some specific Java classes that are needed for our backend to work. And then this backend will load again the Rust part of the Exonum core project And we'll just call some Rust functions using GNI library, pass data, pass some proxy wrappers around structures through the interlanguage barrier. So the structure is rather complicated in this sphere, but overall, we just load a native dynamic library and call some methods just like with any other bindings, for example, like libsodium bindings for Java. Okay, so is it possible to call up on other language, for example, Bash script? Technically, it's possible, but because we do not restrict our users from using any features of the languages. So Java and Rust are both Turing complete, and you can use any external libraries on your nodes. You can run, for example, a Python interpreter on top of your blockchain, and it will work. But you need to take special care to verify the integrity of your database on different nodes, and you need to make sure that your interpreter, for example, will work exactly the same way on different nodes. Otherwise, the consensus will be broken, and you will be unable to use your blockchain. So, is it possible to package our custom Exonum services into containers and run it in the Kubernetes? I don't know how to read, and manage via Helms. Thanks. So, yes, of course. In our examples, we use Docker to package our applications. So you can find some example in our Exonum repository on GitHub. So, for example, we have, I guess, timestamping. Yeah, we have a timestamping example, and we have a special directory called Docker and Docker file here. So any Exonum node is just a plain native application, including Java binding node. So it's pretty easy to install some dependencies that are listed on the website, and just install your application and run it on in any configuration with any tools like Docker, Kubernetes, Helm, and so on. So Exonum applications are not much different from any other traditional blockchain applications, only it runs with traditional application, only it runs with blockchain on the low level. Yeah, thank you. Thank you, Tom. Okay, so does anyone have some questions? I guess it was our first webinar on developing some stuff with Exonum. In my opinion, it was yeah, we can just do it in a better way. We can discuss more important themes for our users, and to do so, we need your feedback. Please send letters to contact@exonum.com or exonum@bitfury.com. You can find our contacts, of course, on our website. So we'll glad to hear some feedback. We'll glad to hear questions. We will be glad to hear some suggestions on different topics to cover with our future webinars. So I guess as we do not have any more questions, we can just finish it right now. Feel free to ask via our emails, to ask on our GitHub, in GitHub issues. If you have some questions on how Exonum works, on how to use Exonum for your specific purposes, and we'll always help you with that. Thank you. Bye.